Hello and welcome you all to this session of Applied Thermodynamics. In the previous lectures, we had discussed about the various modes of work transfer. We had also discussed about the concept of heat transfer and um, regarding the work transfer, we had calculated the PDV or displacement work for different thermodynamic processes. As such, isobaric, isochoric, isothermal, adiabatic, and polytropic processes. So we had calculated the work done. We have derived the formulas of work done for this specific processes. Now, with the help of the discussions we had in the previous lectures and the formulas we have derived throughout this all these lecture sessions, we will be today moving on to solve different numerical problems regarding the concept of work and heat transfer. So before moving on to the first problem, I would like to mention you at the end of the session you will find there is an assignment provided for you. There will be 5 problems in total. As such, the if you face any kind of problem regarding the solution, you may contact me by the email ID which I will be providing later. I have also provided in the previous lectures, still I will provide it today. So let us move on to the first problem which we have for today. So let us start discussing about the numerical on work and heat transfer. So the first problem is provided here. An engine cylinder has a piston of area 0.12 meter square and contains gas at a pressure of 1.5 megapascal. The gas expands according to a process which is represented by a straight line on a PV diagram. The final pressure is 0.15 megapascal. Calculate the work done by the gas on the piston if the stroke is 0.30 meter. Now here we can see, so the area of the piston is 0.12 meter square. So this is the initial pressure. Okay, and after the expansion process, the final pressure is 0.15 megapascal and the stroke length is given to you as 0.30 meter. So let us just write down the informations which are available here. So as you can see, I have written down all the information which is available from this problem. The area of the piston is 0.12. The initial pressure is 1.5 megapascal. The final pressure is 0.15 megapascal and the length of the stroke is 0.3 meter. Now your job is to calculate the work done. Now there is an additional information provided to you. So the gas expands according to a process which is represented by a straight line on a PV diagram. So now our primary objective will be to draw the PV diagram and let us see what how it can help to solve the problem. So let us just draw the PV diagram. So this is the pressure axis, the vertical axis, and this is the horizontal axis, the volume axis. Okay, so this refers to P1, that is equal to 1.5, and this refers to P2. Okay, so now since it is already mentioned in the problem that the expansion process takes place by a straight line, so I am just joining these two states by a straight line so that it becomes easy to understand. Now you have this information which is available from the problem. Now you need to calculate the work done. So here we have our thermodynamic diagram, and from the concept of work transfer we know that the area under PV curve is defined the defined as the work transfer. So simply I can join, I can drop a perpendicular here and a perpendicular here. Now it is quite obvious that the area under, I'm sorry, I would like to use a different ink here to, so the area under this curve will be the net work transfer. So we need to calculate this whole area. Okay, now see that I can draw a straight line which connects this point 2. Okay, and let us just remove these things so it can be much more mm, brighter to understand, brighter to see and easy to understand. So now you can see that the area of work transfer is now divided into two parts, a triangle and a rectangle. Now for the triangle, this is our base, whereas this is our perpendicular height. And for the rectangle, this is our breadth and this is our length. Now the information which we don't have is the base of this triangle and the length, I'm sorry, and the length of this rectangle. So we need to know what will be the value of this length. So from where we can find this information? We can find this information from the calculation of swept volume. That means the volume by which the piston has been expanded. So the volume by which the piston has expanded through. So how we can calculate this swept volume? It is very simple. It is the area and the stroke. That means if we multiply the area and the stroke length, we will find the volume by which the expansion has taken place. So let us just multiply 0.12 into 0.3. Okay, so this will give us the value of this swept volume. So we know this, so let us just name this point as A, this point as B, and this point as C. So we know the length of the straight line 1A is P1 and the length of the straight line 2B is P2. So for the calculations of this area, so let us just move on to the calculations of the area of this thermodynamic curve. Okay, so it will be, so just write W is for the work transfer, so it is the area of 1 to C. Okay, so this is for the triangle and this is for the rectangle, so which will be, we can write A B to C. Okay, so I'll be not writing the informations. Okay, I'll be just referring to the basic data. Okay, like I will write P1, P2 and V. So this is our V. Okay, so this will be half into So this base is V, and what will be the length of this C1? It will be A1 minus AC, and we know that A1 is equal to P1, AC is equal to P2. So C1 becomes P1 minus P2. That is quite simple to understand. So P1 minus P2, and for the rectangular part, it will be V into P2. Okay, so this is your breadth here, which is equal to P2, and this is your length here, which is equal to V. So ultimately the result becomes half P1 plus P2 into V. So now you know P1 as 1.5, P2 as 0.15, and V is calculated from here. So just put on the data here and you will find the net work done. So I hope you have understood the problem. So the basic understanding for this problem lies on the concept of work transfer, which is nothing but the area under the PV curve. So if you have the concept of this simple, this so you need a very simple concept of area under PV curve denotes work done. So this concept is enough to solve this problem, and obviously you need to understand the volume by which the piston has been expanded or the gas has been expanded. So that depends on this area and the length of the stroke, which can be easily found by multiplying the area and the stroke. So I hope you have understood this problem. So now let us move on to the next problem. Okay, so let us move on to the next problem. So as you can see, I have just written down the basic information for this problem. So let us just first read this problem, and I will explain you why I have written this things. So a mass of 1.5 kg of air is compressed in a quasi-static process from 0.1 megapascal to 0.7 megapascal, for which PV is equal to constant. Okay, so this is the information which is primarily given to you. The mass of the compressed gas or the air is given to you here as 1.5 kg. So you can easily understand m equal to 1.5 kg is compressed in a quasi-static process from 0.1 megapascal to 0.7 megapascal. So this is your initial pressure, which I have written P1, and this is your final pressure, which I have written as P2, and it follows a process where the multiplication of pressure and volume, that is PV, it remains constant throughout this process. So we know from our basic understanding that whenever in a process PV equal to constant, it suggests that PV is equal to constant, then obviously it is nothing but an isothermal process. And here the initial density of air is given to you as 1.16 kilogram per meter cube. Now the question is to calculate the work done by the piston to compress the air. Okay, so let us see how we can solve the problem. Okay, as you can see, this is obviously an isothermal process, and by virtue of our information and the class which I had taken previously, which we had discussed in the previous lectures, that the work done in the isothermal process can be calculated by this formula. This P1 refers to the initial pressure, V1 refers to the initial volume, and this is the ratios of initial and final pressure. So now you have to remember that the formula which we are using here, it is the work done in isothermal process for the compressed air. So air is our system here. Okay, so we are calculating the work done for air. Okay, so this has to be specifically mentioned to you, because if you don't understand which is your system and whose work are you calculating for, then it may rise, there will be some conceptual problems. It will be creating some conceptual problems regarding the misunderstanding of system and surrounding. So it is um, extremely necessary to understand which is your system and which is your surroundings. Okay, so we are calculating work for air. Air is our system here, not the piston. Piston is acting as a surrounding here. Okay, so since piston is applying some amount of force on the air to compress it, for piston it has to be positive work, because surroundings is your piston and system is your air. So piston is applying some pressure on the air to compress it. So let us not get into that. Let us see what are the informations which is available to us. So if we want to solve the problem using this formula, then we need to find out what are the informations which are available to us. We know the values of P1 and P2. So the only unknown here is V1, which can be simply calculated from the ratios of Pm by rho. Okay, so the initial density, so let us write just rho 1, so it will help to understand, because after the compression the density of air will obviously change. So rho 1 is equal to 1.16. so the V1 value you will get, it will be m by rho 1, m by rho 1. So ultimately you will get a value of 1.29. That means 1.5 divided by 1.16 is the value of 1.29. So this is your initial volume. Now if you put the values, P1 as 0.1 megapascal and P2 as 0.7 megapascal and V1 as 1.29 meter cube, then you will find a result of minus 251.02. So this is in kilojoules. Now see, the answer has come in terms of minus. So this minus is very important. So work done for air, work done by air is minus 251. But the question is to calculate the work done by the piston. So for the piston, it is the surroundings. I'm sorry, I may have been bit I'm just complicating things, so let me tell you frankly. Air is our system here, piston is our surroundings here. So if work is done by the surroundings on the system, then we term it as negative work. So that is what happening here. That means the work, negative work, suggests that the work must have been done by the surroundings, which is piston in our case. So for piston, for the piston, the work done will be positive. Okay, so for piston, it will be positive. That is what I am trying to explain. So it will be positive work of 251.02 kilojoules. So it was a quite simple problem, but the understanding of system and surroundings is very much necessary here to solve the problem finally. Okay, so I hope you have understood the concepts of work done. Now we shall be moving on to the next problem, and let us just discuss the problem so that your concept and fundamentals become very much strong. So let us just move on to the next problem. So let us move on to the problem number 3. As you can see, I have written down the initial information which is available from the problem. So the problem states that a mass of gas is compressed in a quasi-static process from 80 kilopascal 0.1 meter cube to 0.4 megapascal 0.03 meter cube. Assuming that the pressure and volume are related by, so you must read this one, PV to the power n. Okay, PV to the power n equal to constant. Find the work done by the gas system. Okay, so we are going to calculate the work done by the gas system. Now the informations which are available here, pressure 1, that means the initial pressure is given as 80 kilopascal. The initial volume is given as 0.1 meter cube. The final pressure is 0.4 megapascal and the final volume is 0.03 meter cube. So here I have just converted this megapascal into kilopascal. You know, 1 megapascal is equal to 10 to the power 3 kilopascal. So now since the process follows PV to the power n equal to constant, then obviously this statement will uh, verify here. This statement is quite valid here. So P1 V1 to the power n is equal to P2 into V2 to the power n. So from this equation we can easily calculate the value of n, and we know that this is an example of polytropic process. So work done in polytropic process. So work done in polytropic process is nothing but, by this we can calculate the work done in polytropic process using this simple formula. Okay, so n minus 1. So this n is the only unknown here. Now we can easily calculate this n from the from this equation. So simply taking logarithm on the both sides, we find that n ln of v1 by v2 becomes equal to uh, ln of p2 by p1, which will give us the value of n equal to 1.33. Now putting the value of n equal to 1.33, will so we will get a value of 12, obviously minus 12 kilojoule. That means 12 kilojoules of work has been done on the gas to compress it from 80 kilopascal to 0.4 megapascal. So ultimately this is the work done, minus 12 kilojoules. Okay, so I hope this was a very simple problem. You just uh, need to calculate the value of n, and you must have understood that this is an example of a polytropic process, and you just need to remember the formula of the polytropic process, the work done in polytropic process. So this was the formula for work done in polytropic process that has been followed here, and this was the only unknown which we have calculated from this equation. So we are dealing with very simple problems here. So let us go into a much more complex problem here, where the concept is obviously simple. There is nothing such complex in the problem itself, but the calculation will be little bit complex in the next problem. So let us move on to the next problem. Let us see what it has for us. So as you can see, the problem here, I have already told you that this will involve a lot of calculations. So a system of volume V contains a mass m of gas at pressure P and temperature T. the macroscopic properties of the system over the following relationship. Okay, so the relationship is given to you here, where A, B, and R are the constants. Obtain an expression for the displacement work done by the system during a constant temperature expansion from volume V1 to volume V2. Calculate the work done by a system which contains 10 kg of this gas expanding from 1 meter cube to 10 meter cube at a temperature of 293 Kelvin. Use the values of A equal to, and the values are given here. So as you can see, the gas is following this equation. Okay, so this is the primary equation which is available to us. Now what are the information which is given here? Like the mass is given as 10 kg. Okay, so here you can see that contains 10 kg of this gas, so the mass becomes 10 kg, which expands from 1 meter cube to 10 meter cube. That means the initial volume is V1 and the final volume is V2. So the expansion takes place at a constant temperature of 293 Kelvin. So the temperature remains constant throughout this process and it is equal to 293 Kelvin. So the gas follows this equation, P plus A by V square into V minus B is equal to M at T. So from this equation we have just simplified the value of P. So we have expressed P in terms of all the other variables present. So specifically we have expressed P in terms of V because it will help us in this equation. So we know by virtue of our discussion on displacement work, we know this is the basic formula. This is the fundamental formula which is already provided to us, and we have already discussed about this formula and how we can derive this formula for displacement work. So since P has been expressed in form of V, we can easily replace. So let us just write down WD as the displacement work. So it will be something like this. So V1 to V2. Okay, so just write MRT by V minus P minus A by V square dV. So you have to integrate this equation. So if you integrate this, simply you can understand MRT and A, they are all constant. So they have nothing to do with the integrated value. So I am just okay. So if we integrate, so I am not going on to the integration part because it will take a lot of time to explain. So finally you will get a result of ln v2 minus b by v1 minus b. Okay, and you will get a into 1 by v1 minus v2. Okay, so this is a simple problem which involves a lot of calculation. Lot of elementary calculus is used to solve this problem. So now you have all the data available here. You know mass, which is equal to 10 kg. You know R, the universal gas constant. It is equal to 0.278 kilojoule per kg Kelvin. You know the temperature, it is 293. The expansion process was a constant temperature one, so the temperature remains constant and it is 293. You know the values of V2. The V2 is given as 10 meter cube, V1 is given as 1 meter cube. You know the value of B. B is given as 1.07 into 10 to the power minus 2 meter cube. So easily you can calculate this form, and if you calculate in a better way, in a sharp way, I hope it will give you a result of 1.74 megajoule. Okay, so this will be the work done by this process. Okay, 1.74 megajoule. I hope that uh, we have covered a lot of problem regarding work transfer mainly. We haven't discussed about heat transfer. In the next chapter, in the next lecture sessions, when we'll be dealing with the concept of first law of thermodynamics, we will see problems which incorporates both heat and work transfer. So since heat and work are the forms of energy in transit, so we'll see a lot of problems involving these two variables, these two energies in transit, in the first law of thermodynamics. So I hope these problems will help you understand the problem, the nature of the thermodynamic problems which we face in work and heat transfer. So so let us show you what you need to do. So this is the assignment part for you. So there are 5 problems. Most of the problems are mm, on the type which we had just discussed. We had discussed almost 4 problems, and here you will see there is a problem which involves heat transfer. So this problem 1 is specifically a problem of heat transfer. So I haven't dealt with heat transfer problems, but I hope this is very simple. This is school level physics. You need to understand the school level physics to solve this kind of problems. Okay, and the rest of the 4 problems we have discussed in many forms. I'm sure you will be able to solve the problem. Okay. Mm, so I hope you have a good view on the assignments, and if you can't, you can easily pause here and see the problems. So I hope you have understood all the concepts. The concepts are easily dealt with on the heat transfer and work transfer. And with this good note, I would like to end my lecture session. And I would like to mention that we have completed our lecture sessions on the module 1, and we shall move on to the next module, which is on the first law of thermodynamics. So we shall be discussing the first law of thermodynamics for open system as well as closed system. Okay, so let us end it here. Thank you for your time, and I hope that you have understood the concept of work and heat transfer very well. So let us see you on the next lecture session, which will be discussed primarily on the concepts of first law of thermodynamics. So have a good day. Thank you.